So what do you think about this first one?
Separately.
Definitely separable, and definitely, it's very importantly, not first order linear, right? That exactly, the y squared definitely makes it impossible for that to be first order linear. So yeah, this one is definitely separable. And we can see that if we isolate the y prime, we get y prime equal to, oh, there's Caroline. Hey, Caroline, we're just talking about this first question here, where whether or not this first differential equation is separable or first order linear. And even though it's kind of written in a way that's supposed to kind of make you think that it could be first order linear, right? It's kind of got that first order linear pattern. It's definitely not first order linear because of the y squared right there. So, oh, and let me give you the attendance form as well while I'm thinking about it. It'll show up here. Oh, it's probably over there. There it is. Let me grab that link for you. Oh, there you go. So yeah, this one definitely is not first order linear because of that y squared. So if we want to separate it, Reed, let me know. No worries, totally works. You're welcome to type questions in the chat if you want to, or unmute yourself if you feel like there's something you want clarification on. Just let me know. A little blurry, but that's all right. So let's see. So if we're trying to see that it's separable, we isolate y prime, we bring everything else to the other side. So we've got xy squared minus 6xy. And the idea here is that we want to separate the x from the y. So I'm either looking basically for some power of x or some function of x or some function of y that I can factor out from the rest. Here, I'm not going to try factoring out a y, even though I could because there's a y squared there. I'm going to factor out the x. So I'm going to rewrite this as y prime equal to x times y squared minus 6y. I'm not asking you to solve it, I'm just asking you to show that it's separable. If we were going to try and separate it, this one would actually be kind of a pain, because if we did separate this, we'd have 1 over y squared minus 6y e dy equal to x dx. And solving that left-hand side would actually require partial fractions, right? Because that bottom part factors is y times y minus 6. I don't think your teacher is really going to go there, but I guess he could. I haven't seen any problems like this yet.
Well, there on the homework, there was the I think it was problem 5.
Mhm.
We had to do integration by parts twice.
Sure.
Equal to itself. And he's like, I'm never gonna do that to you.
Sure. Yeah. He seems like he's not going to like ask you just straight up easy questions, but they're not going to get too terrible. Yeah. So I would say let's just leave it at that and say we've shown that it's separable. We could do this later on. Oh yeah. Okay. So yeah. This next one here for y prime plus 2xy over x squared plus 1 equal to 5x to the fourth plus 3x squared. Find the integrating factor mu of x equal to e to the integral p of x. So first of all, to do this problem, we have to recognize that's first order linear. It definitely is. You've got your y prime. You've got right here your p of x times y. And over here, you definitely have your q of x. But if we were going to rewrite this in the way that I think is probably more correct, I would want to rewrite this as y prime plus 2x over x squared plus 1 times y equal to 5x to the fourth plus 3x squared. Just to really separate the function of, oh, sorry, you can't quite see that. To separate the function of x from the y that's being multiplied by. So it's a little more obvious that we don't have that y in there. And then if we're going to find the integrating factor, that's going to be mu of x is going to equal e to the integral of 2x over x squared plus 1. This is something that's not too terrible to integrate. It does require u substitution, or at least thinking about u substitution. That's right. So if we're going to look at this, if we're going to do the u sub here, we would let u equal x squared plus 1. Du would be exactly 2x times dx. So that integral becomes the integral of just 1 over u du. Or if you prefer, du over u. I prefer 1 over u du. And then integrating that, we're going to get the natural log of, again, when we're dealing with integrating factors, we don't worry about, I mean, really in this class, we don't worry about the opposite value ever, kind of, at least in this, I should say, when we're talking about differential equations, we never really worry about the opposite value that pops up when you integrate 1 over u or 1 over x. So I'm just going to write the natural log of u, even though it feels wrong. And then that's going to be the natural log of x squared plus 1. So this is going to end up being e to the natural log of x squared plus 1, which is going to equal x squared plus 1. So here our mu of x or our u of x integrating factor is just x squared plus 1. It's kind of nice, works out all right. Questions about that at all? Okay, cool. So let's actually continue with this one and solve this differential equation, right? Yeah, I've got it over here. So let's find the solution to that same differential equation, which I kind of, right? Oh no, I changed it up a little bit. Because I realized that right, yeah. Let's write this again, because I realized that integrating factor, the q of x on the other side there was not going to be very nice. I thought it was going to work out to be something, and it was something else there. So let's do a similar problem. Let's solve the following differential equation: y prime plus 2x over x squared plus 1 times y equal to, what have I got here? 12x cubed, with the initial condition that y of 0 is equal to 13. And since we just found it, let's go ahead and just remind ourselves, we just found the integrating factor mu of x to equal x squared plus 1. And just so that I'm absolutely certain here, your teacher has explicitly said like he wants you to just go straight to like finding the answer and not doing all like the product rule stuff. Okay, so from here we jump straight. I think it's a good idea if you're doing that to make sure you're very explicit and be like, okay, there's my p of x. I've got y prime plus p of x times y, and there's my q of x. Just so you really know what's what. And then I like to then, if I'm doing it this kind of shortcut way, I'm going to write out that my solution, y as a function of x, I like to write the general formula first, right? That it's, or I should say the formula with just like the names of the functions in there. So that's going to be 1 over mu of x times the integral of q of x times mu of x. And then substitute in all the functions that what we know. So that's going to equal 1 over x squared plus 1 times the integral of q of x, which is 12x cubed times x squared plus 1. This one's not going to be too terrible, but sometimes this will end up being integration by parts a couple times, or maybe a use substitution. But integration by parts is probably the most likely culprit you'll see here, because often this function and this function kind of have nothing to do with each other. Especially if one of them's trig, it's very likely you're going to get integration by parts. So let's do this. So simplifying this, I've got 1 over x squared plus 1 times the integral. If I distribute this 12x cubed, I'm going to get 12x to the 5th plus 12x cubed. I guess I could factor out the 12, but I don't actually really want to, because I recognize that when I anti-differentiate these, the powers are going to work out nicely. So I wouldn't bring out the 12 here. So let's do the work. I'm going to get 1 over x squared plus 1 times, let's see, 12x to the 6th over 6 will be 2x to the 6th. And 12x to the 4th over 4 will be 3x to the 4th plus c. And I don't really think you need to distribute the 1 over x squared plus 1 here. I mean, it's really just a matter of taste at this point. How do you want to write your answer? But we do need to still find the constant c. So find c by using the initial condition. So we're going to plug in x equal to 0 and y equal to 13. Oh, by the way, right, we should still be saying, right, I suppose, y of x equals 1 over x squared plus 1 times 2x to the 6th plus 3x to the 4th. Let's see. Okay, well, it's not too bad. Luckily, it's an x equals 0, so pretty much everything's just going to go away, and you're going to have, let's see, y is 13 equal to 1 over 0 plus 1 times 0 plus 0 plus c. Okay, well, that was easy. C is 13. I will say this every time. You can't stop there if they're asking you to find the solution. We then have to go back and be like, okay, so our particular solution, or just our solution they're asking us for, is the same y of x, but now with the c value plugged in. So if I was writing this, I'd probably write it as a fraction. I'd probably write it as 2x to the 6th plus 3x to the 4th plus c, all divided by x squared plus 1. And be careful. Sometimes it's fine to, like, especially if you're working in web work, sometimes they'll give you the y of x equal to part, and you'll write what the the function's equal to, but sometimes they'll say, write the solution, and you'll have to write the y equals part as well. There was definitely, I think, one problem like that in the previous assignment where people were getting stuck because like, oh, they had to write the y equals as well. So just remember that when you're finding solution to a differential equation, the solution really is y equals to this function. Someone's calling me, they don't matter. Okay, so yes, here, sorry, that was number 2. Any questions about any of that? I can zoom out just a tiny bit here. Cool. All right, let's move on. I think I've got one more like this, and then we'll do some word problems. Yeah, not you. Cool. Yeah, let's do this one. Okay. Yeah. I was getting creative with some of these first order linear problems. So let's solve the following. We've got dy dt plus y times cotangent of t is equal to t. And we've got an initial condition, assuming I didn't make any mistakes here, of, I'm really actually, yeah, that's fine. Yeah, of y of 3 pi over 2 equal to 5. Okay, so solve. So let's see, we could, usually if it's written like this, you should probably make the assumption that the person is either giving you something that's obviously first order linear or trying to trick you. I don't think your professor is particularly tricky. Like, I don't think he's trying to trick you most of the time. I think this guy is usually fairly straightforward. So if I saw something like this, I would start with the assumption that it's probably first order linear. I would double check. I would be like, okay, I've got my y prime. I've got my y times my p of, I'm going to write p of t instead of p of x because my variable is t instead of x, no big deal. And I've got my q of t here. Great, everything's looking straightforward. So p of t is cotangent of t. And then our integrating factor, mu of t, is e to the integral of p of t, which is e to the integral of cotangent of t. All right, Reed, let me ask you, do you remember how to integrate cotangent of t? What is it?
It's the integral of cosine over sine.
Cool. It is an integral that you are allowed to memorize, although you certainly do not need to memorize it if you remember to rewrite it as cosine over sine, because then we can do a u substitution. So if we let right here, I'll use green. I never use the green pen. We let u equal sine of t, and you'll when you're integrating either cotangent or tangent, and you write it as sine over cosine over sine, depending on which one you have, you always want to let u equal the bottom part. So here we're letting u equal sine of t, and our du is exactly the derivative of sine, which is cosine times dt, which is exactly what we've got up top here. So our integral of cosine of t over sine of t dt once again becomes the integral of 1 over u du, which is just the natural log of the absolute value of u. Yeah, I'm going to write the absolute values this time. Why not? Which is the natural log of the absolute value of sine of t. It is not uncommon to see a lot of integrating factors where you get e to the natural log of something, so that the e and the natural log undo each other and you just get the function. So here, our integrating factor ends up equaling is e to the natural log of the absolute value of sine of t, which is just going to be the absolute value of sine of t. And I guess actually, no, I'm just gonna say just sine of t. We're just gonna ignore the absolute value. This is the way to get. Okay, so then we jump to the solution. The solution is going to be that y of t is equal to 1 over mu of t times the integral of q of t times mu of t. When you write this out, if you write it out this way, I do encourage writing the q first, just so you don't happen to fall in the mistake I used to make of wanting to cancel the mu's. We know they don't cancel, but this helps me remember that, oh yeah, they need to multiply out before we cancel. So let's see. So this is going to be fun. My y of t is going to equal 1 over sine of t times the integral of q of t, which is just t, times sine of t. And here we do need to use integration by parts. I know, but it's only a one-step integration by parts, right? At least it's not t squared. So, in fact, I'll remind you, there is tabular integration, which I'll remind you of in a second if we want to. So let's see here. So our u is going to equal t. Our du is going to be 1 times dt. Our dv is the rest, which is sine of t dt. And our v is the antiderivative sine of t, which is cosine of t, negative cosine of t, sorry. So then this is going to end up equaling 1 over sine of t, which I might write as cosecant. I might wait to write it as cosecant. So 1 over sine of t times, let's see, the integral of t sine of t is going to be u times v, so negative t times cosine of t, minus the integral of v du, which is negative cosine of t dt. Now, if it were me, which it is, I would see a minus and just make those both pluses. So plus, and then we're going to write this as 1 over sine of t times negative t cosine of t plus the antiderivative of cosine is just sine of t plus c. Here, I do like the idea of distributing the sine, the 1 over sine personally. I mean, you can leave it like this. That would also be fine. You could write like this, or you could write, I'm thinking, you could write like this, or before you distribute, you might want to find your c value, I guess. So let's find c. So that's my y of t. And then we're going to say that y of 3 pi over 2 is 5. So we're going to set y equal to 5 and t equal to 3 pi over 2. Ooh, okay, what's sine of 3 pi over 2? Negative 1. So we're going to get 1 over negative 1 times cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. C is c. So it looks like we've got 5 equal to negative 1 times c minus 1, or negative 5 is equal to c minus 1, or negative 4 is equal to c. So our one way of writing our particular solution here would be to write that y of t is equal to 1 over sine of t times negative t cosine of t plus sine of t minus 4. Instead, I can probably squeeze it down here. Or if you wanted to distribute the 1 over sine, 1 over sine times cosine is cosine over sine, which is cotangent. So you can write this as y of t equal to negative t times cotangent of t. And then 1 over sine times sine is just going to be 1. And then 1 over sine times negative 4 is negative 4 over sine, which is negative 4 cosecant of t. Mostly I point this out for the reason I often point this out is that while you might not want to write it like this or not care to write this, your book might write it like this. And you're trying to compare solutions, it's good to see that this and this are the same. So cool. All right. I alluded to something just a second ago that I feel like I should clarify. So if you end up getting some sort of first order linear problem like this, and you have to do integration by parts a couple times, it will probably lend itself to the tabular method I think we talked about last quarter a little bit. So I'm going to make up an example here that's going to be fairly straightforward. Sure, fairly straightforward. Let's do that. Yeah, sorry, I'm trying to think about like how to. Sure, it doesn't need to be perfect. So let's just say we have this. Let's say we have y prime plus, sorry, I'm making stuff up here. Sure, let's just make it real easy. Let's say we have, trying to make it real easy. It's not my forte is making things easy. Let's see, e to the natural log. Okay, sure, that'll be a t. All right, sure. Let's say we had like a 6 over t times y equal to, sure, let's do t squared cosine of t just to make life tough. Okay. So let's say we were going to solve this. We might not finish solving it. Well, we'll probably finish solving it. It's not too terrible. I mean, it is, but it isn't if we know the trick. So if I was going to solve this, step one, I recognize it's a first order linear differential equation, and I find my integrating factor. Mu of t is going to be e to the integral of 6 over t dt. I suppose I should be thorough here, right? I'm just going to remember that there's my p of t. There's my q of t. Something to be extra careful about, if you have a y prime minus something times y, that minus sign needs to get sucked up in your p of t. And does make a big difference, right? E to the negative something is way different than e to the positive something. It's the, right. Right, exactly. Right. If you find yourself getting to a place where things are getting a little wacky, go back and check your work. There was another problem I saw posted on Piazza where a student was asking, like, I got to this integral, but I really don't know how to do it. And it was something like t squared e to the 3t squared. And the was that you?
No, it wasn't.
Oh, sure. Right. But the problem was, well, one, you can't integrate e to the 3t squared, so it's not going to work for integration of parts. But the real problem was there was a step back from the beginning when they multiplied both sides by t when they should have divided both sides by t. So just be careful with the work. If you see something getting crazy, it's very likely that there was an error back before, because usually most of these problems are usually intended to work out pretty straightforwardly. So if something isn't, it's a good indication that there might be an error somewhere. Let's see. So this one's not too bad. E to the integral of 6 over t is just e to the 6 natural log of t. Yeah, yeah. And then oh wow, I made this. Oof, oh god, this is, oh my gosh. I'm gonna change that 6 to a smaller number because that's gonna get real terrible. I'm gonna rewrite this one because I just made myself like a 9-step integration by parts problem. Let's try making this slightly less awful. Let's say we have y prime plus 2 over t. Oh my gosh, 2 over, oh my gosh. Let me, can I write anything here? Try this one more time. Okay, sorry about that. I was like, this is gonna get out of hand. Y prime plus 2 over t y equal to, let's make sure this t times cosine of t. Okay, that won't be quite as wild. Last one was about to be something super crazy. So if we do this one instead, then our integrating factor is going to be mu of t equal to e to the integral of 2 over t dt, which is e to the 2 natural log of t, which is e to the natural log of t squared, which is just t squared. Okay. So then our solution is going to be that y of t is equal to, again, I'm really a fan of always writing it out. You don't have to, but I like to. So I'm going to get 1 over mu of t, which is 1 over t squared, times the integral of q of t times mu of t, which is going to be t times cosine of t times t squared dt, which if I simplify the integrand just a little bit, that's going to be 1 over t squared times the integral of t squared times t is t cubed cosine of t dt. Right, it would have been completely insane. So what I'll tell you about this is that I think it would have been 8, right? You add the powers, right? It would have been 8 steps. I mean, still terrible either way. So here, this would be a 3-step integration by parts problem, which, although doable, there's a lot of room to make easy mistakes, and it's very likely that anyone doing this the long way would make an error somewhere. But for integrals like this, where it's t to a power times either cosine or sine or e to the t, right? Those are the 3 things you can do this for. It doesn't work for anything else. But if you have t to a nice positive integer power, or x, or whatever variables, times sine or cosine or e to the x, totally works. And what you do is you write your u column and your dv column. And in the u column, you pick the thing you would pick for u. So our u would be t cubed. Right? That's right. Remember, u is equal to late. You pick a logarithm. If you don't have a logarithm, you pick an any power of x, and we have an any power of x. So that would be our u, and the rest would be our dv. So we write our u column, and then in the u column, we take derivatives, because when you do this u dv integration by parts thing, you're always finding u and then du, which is the derivative of u. and you're finding dv, and then v, which is the antiderivative of v. So for the u's, you take all the derivatives until you get to 0. So 3t squared, and then 6t, and then 6, and then 0. And for dv, you start with your choice for dv, which was cosine of t, and you take all the antiderivatives. So I want to make sure everyone's clear. This direction we are differentiating. And this direction here, we are anti-different. I should say this side. It's the same direction. We're both different. On this side, we're differentiating. On this side, we are anti-differentiating. Which can be a little dicey with cosine because you have to remember which way the signs go. So the antiderivative of cosine of t is positive sine of t. The antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. And the antiderivative of negative sine completes the cycle and we get back to positive cosine. That doesn't always happen, but since we had so many steps, it did. And then you go from upper left to lower right. So you go that way, that way, that way, that way. So you're going to get 4 pieces because there's 4 arrows. And it's plus t cubed times sine of t minus 3t squared times negative cosine plus 6t times negative sine minus 6 times cosine. So our answer ends up being 1 over t squared times all that. So positive t cubed times sine of t minus 3t squared times negative cosine, then minus signs cancel. So it's again a positive 3t squared times cosine of t plus 6t times negative sine of t. So it's going to be a minus 6t times cosine of t. Sorry, oops, sine of t, darn it. It's a sine of t. Terrible, terrible, terrible. And then minus 6 times cosine of t. Plus c. And I would not bother to write that to simplify that, although you totally could distribute the 1 over t squared. Just to be clear, that's a sine of t. In case it's not, in case it's hard to read the scribbling I've done there. Okay. So if you encounter something like that where it's t to a relatively large power times cosine or sine or e to the t, then you should do something like, or you can. You don't have to, but you can, and I would. All right, cool. Let's look at a couple word problems because there's definitely some word problems in your homework. And the hard part about word problems usually isn't solving them so much as being able to get them to the place where you can solve them in the first place. So let's look at this example I've got here. Already written out ahead of time because being efficient. So assume that the volume V measured in inches cubed of a weather balloon is a function of pressure. Pressure being the variable P measured in pounds per square inch. Which seems always kind of like, I have a problem with this problem already because when I'm thinking about the volume of a balloon, my brain automatically says, oh, it's a sphere, volume equals 4/3 pi r cubed. We're not going to use that at all here, even though like it feels very much like that's what I would want to do. I have another problem with this as well, which we're starting to see. And that the rate of change of V is inversely proportional to the volume V. So they're saying that the rate of change of the volume changes as the pressure changes, which is why they're writing dV dP down here. Normally, if I was saying, like usually when I think about a rate of change, I often think like dV dt, because I'm thinking about how the thing is changing as time is changing. But that's not always going to be the case. So just something to think about. So they're saying that the rate of change of volume is inversely proportional to the volume V. And that's enough information to actually write the differential equation down. So the rate of change of V, which is dV dP, so that's my rate of change of volume, is inversely proportional to the volume. So if it was just proportional, I would say it's equal to K times V, because it would be just proportional. But it's inversely proportional, meaning it's equal to a constant, right? That's the proportional part, times the inverse of V. So there's my proportional to part. And there's my inversely part. Okay, so that's it. That's all that is required as far as writing the differential equation. It's just finding how to relate how the thing is changing to what they're saying. We're basically taking their words and figuring out what they actually mean. The second part, solving this is, the solving part is not too terrible here. We're going to solve this. Well, it's definitely looking like it's separable to me. Although you couldn't. It's definitely not first order linear. Specifically, it's not linear, right? Your function v is non-linear when you've got this inversely proportional part here. So I'm going to solve this by separating variables. So I'm going to have v times dv equal to k times dp. And then we're going to integrate both sides. So on the left-hand side, we're going to get v squared over 2. On the right-hand side, we're going to get k times p plus a constant c. And then if we were solving for v, so it's interesting here because like you can try and start to solve this at any kind of juncture you want. When I say solve, I should say, if you know you're going to be finding your constants, you can kind of start plugging them in whenever you feel like is the right time. You might start now. I probably wouldn't. So if I start actually trying to solve this, well, I'm going to isolate v. So I'm going to say v squared equals, now if I'm multiplying a constant by 2, it's still a constant. If you like, I can be more specific and say there's my k1 and c1. If I multiply everything by 2, I'm going to get v squared equal to 2 times k1 is a new constant k2. And 2 times c1 is a new constant c2. Is this the right time to find my constants? Probably not. Maybe it is. I don't know. But I'm thinking if I'm actually going to plug in these pieces of information, pressure equals 10 when volume equals 40, and pressure equals 15 when volume equals 30. I probably don't really want to be squaring 30 and squaring 40. I mean, I might. It's not that terrible, but I would probably go ahead and solve for these. So I'm going to say that v equals, now technically when I take a square root of both sides, what do I get? Right. Now the thing is, that's actually not a function, right? Because if you've got two possible outputs for one input, not a function. But the thing is here, our initial conditions fully determine whether it's going to be positive or negative. So since v has positive values, which makes sense for a volume, right? You can't really have a negative volume. There's certainly other things that we measure that can have negative values, but here v has to be the positive square root of all this stuff because you can't have the negative values for the volume. So then if we plug in p equal to 10 and v equal to 40, I feel like these numbers, these numbers just seem a little extra bigger than I meant them to be, but that's all right. No, they come out to be gross. Okay, that's totally fine. Sometimes numbers are gross. Interesting here. Cool. Sorry, I was looking. So looking at this, it might have made sense to plug things in earlier. I don't, right? So, I mean, it's kind of a mixed bag. Sometimes sometimes it's better to plug it in sooner. Sometimes it's better to plug it in later. It can be kind of hard to tell. But I guess if I'm trying to find, K and C, it might make more sense here than here because if I plug in p equals 10 and v equals 40 and then try and solve for either of these, I'm just gonna have to square both sides anyway. So let's actually go back to here. Let's actually use a new piece of paper because I'm out of room. So we've got v squared equal to k2 times p plus c2. And we know that v equals 40 when p equals 10. Let's plug that in first. So I've got 40 squared, so 1600 equal to 10 times k2 plus c2. I can't really do anything with that other than use the other piece of information. And we also know that v equals 30 when p equals 15. So plugging that in, 30 squared is 900. P is 15. And we've still got C2. So if I was doing this, I might subtract these equations from each other because that's going to cancel the C2s. So subtracting 1600 minus 900 is 700. 10 minus 15 is -5. So it looks like K2 is going to be 700 divided by -5, which is going to be 140, -140. Okay. And then if we go back and plug that in for K2, we should be able to solve for either C2 in either equation. So plugging it back into the first one, because it seems a little easier to do. 1600 equals 10 times -140, that's -1400 plus C2. It looks like C2 is going to equal 3000. Curious. The numbers seem interesting. Let's double check. I'm just double checking my work here. Yeah, totally. Yep, that's it. So now we can go back up here and be like, okay. You might want to see the things I'm writing. If you can't see them, let me know. Sorry. So we end up getting that V squared is equal to -140 times pressure plus 3000. And then we can say that V is equal to the positive square root of, I would probably write this as 3000 minus 140 times P. Or if you prefer, and I kind of do prefer to write it as V as a function of P equal to the positive square root of 3000 minus 140 P. Cool. Not a bad question. Time's up. Okay, we got 10 minutes. Let's do another word problem. I don't think so. I would do more tank problems because I like tank problems and I think they're interesting, but I didn't see any on your homework. So although I think that's fun and interesting, it might not be the best use of our time. So I guess we'll do something else instead. Yeah, totally. I think, yeah, I don't know if I can do anything like it other than just kind of address it fully. Because like I don't feel like there's a way to like really change it. Let's have a discussion about question 7 here. So what have we got? A drug is administered intravenously at a constant rate of R milligrams per hour. And let's also make up some numbers just so we can kind of see this both ways. So if I was going to make up numbers just to try and see if I can make it easier, let's say this is going to be, I don't know, 20 milligrams per hour. Probably a high dosage, but it's made up, so it doesn't matter. And is excreted at a rate proportional to the quantity present. Now I'll point out in the next question, they say set up a differential equation for the quantity Q. So the quantity present is what Q is representing. So this is your Q of T. And then they also say with a constant of proportionality, just so you know what constant letter to use, with K as your constant of proportionality. So I will say that this problem has a hallmark that is similar to the tank problems, which is that you have a system that you are putting things into and taking things out of at the same time. So just like a tank problem, if we're trying to find the rate of change of the quantity present, so if we're trying to find the rate of change of the amount of stuff in the body, the amount of drugs in the body, it's going to equal the amount in minus the amount out. So if you're putting more in than you're taking out, the quantity in the body is probably increasing, versus if you're pulling more out than you're putting in, the body and the amount's eventually going to be decreasing. Similar to, so this kind of is a tank problem. It's just a different way of conceptualizing it. So the first thing is asking us to set up a differential equation for the quantity Q in milligrams of the drug in the body at time t hours. Your answer will contain the unknown constants R and K. Okay, so there's someone else here. Cool. For the person who just joined, please do. Oh, it's just Caroline again. Never mind. There's two Carolines now. Okay, so for this one here, if I'm trying to write this well, the rate of change of Q is just either Q prime. I usually prefer to write dq dt, but either way is fine. All right. So how much drug are we putting in the body? 20 milligrams. So just, yeah. So, and let's actually, so just to point out, it says set up a differential equation for the quantity Q in milligrams of the drug in the body after at time t hours. So we definitely should be thinking about we're putting in how many milligrams every hour. So it makes sense that we should be saying, oh yeah, the amount we're putting in is, I'm going to do, let's use our made up number, 20 milligrams per hour. Yeah, and then so that's what's going in. And how much is going out? So almost always for these tank problems or drug problem in this case, the amount in is usually some sort of constant. Like right when we were doing the tank problem on Friday and we we're putting in, like 3 pounds of salt, or we're putting in like 3 gallons per minute of a 2 pound per gallon mixture, right? You're just putting in a constant 6 pounds of salt every minute, right? That's usually going to be constant. Whereas the amount you're taking out, since you're usually taking out just some amount of the entire system, that's going to vary because the amount of stuff, drugs in this case, or salt in the tank problem, the amount of salt that's in there or drugs that are in there, is going to be something that's changing over time. And so what we're doing is we're saying, well, we're going to take out. Interesting. Yeah. Excreted at a rate proportional to. So for the tank problems, it's easier to think about because you're just being like, well, I'm taking out the same volume at the same time. So if we're excreting at a rate proportional to the quantity present, I believe we're just going to do something like we're going to take out K times Q of T. That seems reasonable. So in the non made up version, we definitely like dq dt equal to 20 minus, you can write the same thing, James. dq dt, okay, right, not 20 this time, yeah, equal to R minus K times Q. I believe that's what our differential equation would look like. We're putting in R milligrams per hour, we're excreting some amount proportional to however many milligrams are in there per hour. Okay. So that doesn't seem like it's too terrible to set up. Solve this differential equation, assuming there's no drug in the body initially. So let's write down what that means. So if I want to solve dq dt equal to R minus K times Q, we also are given, well, if we know that there's no drug in the body initially, that means that Q of 0 should equal how much? Right. And you can write it this way, or if you prefer, you can write it like Q equals 0 when T equals 0. It's another perfectly good way of writing it. And that's the information we're going to use later on to figure out what K is. R is just, so the thing that's kind of challenging about this particular setup here is R is just some given number that we don't know, whereas K is some constant we have to solve for, which is a little weird, right? So, which is why it might be helpful to think of this as dq dt equal to 20 minus K times Q. So often when I'm dealing with like a constant that's made up that I don't want to deal with, I will do this and I'll do all the work with this, and then I'll go back at the end and replace every 20 with an R in this case. It can be a little challenging though, because sometimes you have like this number gets manipulated. So you have to, like, it ends up being 10. So you have to be like, oh, well, that's really R over 2. So yeah. First order linear, separable. You could do either. I feel like this is more geared towards being first order linear. Not that I actually know that. Yeah, I don't have a great intuition about which I usually default towards separable, but I feel like here it might not be the best because let's take a look. So if we were going to do separable, which I don't think we're going to do, but if we were going to do separable, well, there's no t's except for the dt down here. So basically we have to bring all of this 20 minus kq over to the left and the 1 dt over to the right. The problem with this separable one is that you can't really, this is one term. You can't break that apart into two pieces. So you can say dq equals 20 minus kq times dt, and then divide everything by 20 minus kq. And then integrate both sides. And not that it's impossible to integrate 1 over 20 minus kq, it's just, I mean, it's going to be the negative natural log of 20 minus kq divided by k, which is kind of annoying. Let's see how it looks. I mean, let's write, okay, fine. Negative 1 over k times the natural log of the absolute value of 20 minus kq. Not my favorite, but fine. Yeah, that's, or if we do first order linear, so let's see, we're going to say that q prime plus k times q is equal to 20. And k is going to be our p of t, and 20, or r more generally, is going to be our, q is a terrible choice here because q, right? Yeah, that's awful. This is our q. It's fine, we'll deal with it. So then if we were doing this first order linear way, our integrating factor mu of t would be e to the integral of k dt, which is just e to the kt. And then if we're going to write our solution would be that our function q of t, right? That's not the q in quotes, that's our actual solution. It's terrible. You should never use q if you're gonna think you might have to do integrating factor, apparently. That's going to equal 1 over e to the kt times the integral of 20 times e to the kt. All right, so let's see. We're going to get q of t equal to 1 over e to the kt times the integral of 20 e to the kt is 20 e to the kt over k plus c. And if I were going to multiply this out, I would multiply that, and I would say that q of t is equal to, well, 1 over e to the kt times e to the kt cancels, and you just get 20 over k plus c over e to the kt. Funky. And then if you plug in t equals 0 and q equals 0, sorry, I can't do that. Apologies. So I get 0 equals 20 over k plus c over e to the 0. So it looks like that constant there is negative 20 over k. So it looks like our solution here is q of t equal to 20 over k minus 20 over k e to the kt. Which you could, so I don't love the way this is written because you could totally factor out the 20 over k. So you could also write this as 20 over k times 1 minus 1 over e to the kt, or e to the negative kt. And I think writing it that way makes it much, much easier to answer question part C, which is what happens as t goes to infinity. And we can see that it's, oh, I'm way out of time. It's as t goes to infinity, this part's going to go to 0. So this goes to just 20 over k as t goes to infinity. Or in the parlance of the actual question, instead of 20 over K, we're really going to what? Yeah, interesting. All right, I should have stopped talking 3 minutes ago, so I will stop talking now. Good. Right, it definitely is, I think, useful to, I think that problem would have been harder if we'd left R as just R. I think it was a little bit easier changing it to 20. It's interesting though, because I thought we were gonna end up. I mistakenly thought we were gonna end up actually figuring out what K was, but we didn't. That was not part of the problem there. Interesting.